Here with the Jeetcode, we're gonna do some coding. Oh man, I wanna make money so badly. Fuck. I need money. Mode sorted. Okay. Dynamic programming. What is DP? Let's just fuck. This is all easy questions too. That's even the nail in the coffin, so to speak. Just give me the easy questions, bro. Oh, it's gonna be hard question. Okay, let's try hard array question and see how I do it. First missing positive. What's the number? 41. Hard. 41. Hard. Stay hard, nigga. Okay. Okay, let's just give it a go. Given an unsorted integer array nums, return the smallest positive integer that is not present in nums. That is not present in nums. Okay. One is in the array, but two is missing. Okay. What? One? Oh, it's just like 10 is missing. So it's like a rummy, you know. What do you call it? It's supposed to go 1, 2, 3, 4, 5. If it misses, not even like 5, it could be like 6, 7, 8, 9. Instead of 10, it's like 11, 12, and it's missing one number, right? Wait, I don't understand what. So, first missing positive. I want to understand the question. Can you fuck off, please? Yeah, let's just go here. Leak code. What can you fuck off? Okay. First positive. So the way. Okay. Yeah. I got it. Okay. I'm gonna.
Hey everyone, welcome back.
I'm gonna hit people. I wanna punch people. Fuck.
So let's write some more neat code today. So today let's solve first missing positive. This is a hard problem, not because it's hard to solve. There's a variety of solutions. One solution is an n log n solution. Another solution is a linear time solution, but that one takes also linear time memory as well, so time and memory. But there's also a solution with linear time, but it takes constant memory, and that's the difficult solution to create, which is why this problem is categorized as hard. That's the one I'm going to be mostly going over today. So we're given an unsorted integer array of nums.
So yeah, there you go. n/1.
Simply, we just want to find the smallest missing positive integer. What does that mean? Well, my question is, what's the smallest positive?
So who asked this? Facebook? How do I check it? Blind 75 practice. Give me the blind 75, nigga. Sliding windows like so.
Integer in general. What's the
Let's just look into
coding
this.
interviews are hard. So much so that there's nerds out there solving hundreds of leak code.
5, bro, almost 600. When was this? 2 years ago? Now it's like fucking 1,000 quotes, isn't it?
Problems just
Bro, I think I can do
to
this.
get ahead. But is that really necessary? Do we really live in a world where you need to solve cherry pick up a three-dimensional dynamic programming problem just to get a job? I don't think so. Yes, technically anything can come up in an interview, but I think there's a smarter way to prepare. Why not prioritize the concepts that are easiest to learn, but also are most likely to come up in interviews? Well, because most people don't know what those are, but with my background, I think I do. Arrays are the first data structure that we all learn about, and that's because they're simple, but there's surprisingly a lot of non-trivial algorithms relevant to arrays. I'm not just talking about binary search and sorting, but also two-pointers, the sliding window, and if we want to get fancy, we can even do some pre-processing by computing the prefix sums of an array to solve certain problems more efficiently. And the good thing is, most of these algorithms are actually not very complicated once you understand them. But if I were you, I wouldn't just understand them. I would get so good at them that solving a simple binary search or a sliding window problem feels as easy as writing a for loop, even if that means you have to go back and resolve the same easy problem multiple times.
Bro, this is the woodpecker method.
People will struggle with more difficult problems, and that's because they don't have a really good grasp of the basics. And actually, arrays are so all-encompassing that many other patterns can also be applied to them, like stacks, greedy algorithms, and of course everyone's favorite, dynamic programming. Another broad concept is recursive decision trees. You might be thinking, doesn't the specific pattern actually matter? Like, recursion can be applied to trees, it can be applied to backtracking. Well, yes, no one is born knowing those concepts, you'll have to learn them. But if you have a very strong fundamental understanding of decision trees, you can solve a wide variety of problems, from binary trees, backtracking problems, combinatorics, dynamic programming, and sometimes even graph problems. If you've gone through the Jeetcode 150 list or roadmap and watched my videos, you've probably got tired of me talking about decision trees. Decision tree. So we have, but that's because they are such an easy way for us humans to understand the intuition of complex algorithms. Graphs are a massive topic. It's literally a sub-branch of mathematics. That's why some of the craziest problems you might have seen are graph problems. But at the heart of graph problems are two relatively simple algorithms, DFS and BFS. You probably first learned about these algorithms with binary trees, because trees are just a special type of graph. But I really can't overstate how important these two algorithms are. You should definitely be able to apply these two on both matrix graphs as well as adjacency lists. Because even though you may be implementing the same algorithm, depending on the structure of the graph, the code can be quite different. But again, don't just get surface level knowledge. I would recommend you to really understand them. Like, you should be able to tell me what would go wrong if I removed any of these lines of code. Without this, we might get an index out of bounds error. Without this one, we might get stuck in an infinite loop. Without this one, we might overcount the solution. I know some people will say, who cares? This sucks, it's not relevant to my job anyway. And that's a fair point. But I don't think it's bad to be able to deeply understand a pretty fundamental algorithm like depth-first search. The forbidden jutsu of the algorithms world is definitely the hash map. Whether you're using it to count the occurrences of characters in a string or using it to build an adjacency list for graph problems, it's almost certainly going to be useful in your interviews. There's not much to talk about because thankfully hash maps are pretty easy to use, but if you're struggling to optimize your solution, the first question you should ask yourself is, would a hash map be helpful here? Heaps are also pretty simple. They have a sorted property either as a minimum heap or a maximum heap. They support log n time insertions, log n time removals of either the minimum or the maximum element, constant lookup time, and lastly, heapify can transform a set of values into a heap in O of n time. That's relevant because it's more efficient than inserting elements one by one if you're given all the elements up front. We can't end this video without talking about dynamic programming. We all know that it's difficult to learn, but it's not as common as people think it is. I would definitely prioritize it after all of the other concepts I've
So arrays, decision trees, and hash map. Arrays and hash map could be learned together. Decision trees, I don't give a
talked
fuck.
about in this video. But if you are
Don't
going
give
to
a
learn
fuck,
it, I
bro.
would mainly focus on the most common and famous dynamic programming problems, like the longest common subsequence problem, the coin change problem, and several others that are included in the Neetcode 150 list. Yeah, it's theoretically possible you'll get asked a question like cherry pickup 2. Yeah, cherry pickup 2, because the first one wasn't hard enough. But let's be honest, even if you've literally solved this problem before, there's still a high chance you won't be able to solve this in a real interview. But that's all I really wanted to talk about. I see a lot of people nowadays solving hundreds and hundreds of problems, and there's nothing wrong with that, but if your goal is just to prepare for interviews and maximize your chances with the least amount of effort possible, like doing a reasonable amount of preparation, I would highly recommend focusing on the most important concepts that I talked about. Coding interviews are hard, so much so that there's nerds out there solving hundreds of LeetCode problems just to get ahead.
Bro, every solution is low-key kind of hard. Okay, let's just... I'm not gonna do this. Let's... Only easy, bro. Only easy. This is a bad strategy. For pattern recognition or anything, it's just like bad. Pretty bad. Remove duplicates. 2-point. How do I do a 2-pointer? Fuck. I don't know how to do a basic 2-pointer. What's the valid palindrome? Let's just... This is how you like learn too. So I ain't even man. So is it a valid palindrome? So what are the topics again? Valid palindrome. I think the way you go about it is... Fuck, I just need to look at the solution again. It is what it is, bro. That's the game.
Hey everyone, welcome back, and let's write some more Neetcode today. So today let's solve the problem valid palindrome. I'm actually going to be solving this 2 different ways, and I think both ways are definitely going to be helpful to know. Also, we're going to just iterate through every single and have Python at least does, and we add it.
Yeah, he's doing like an alphanumerical way to do. But can you not do it in any other way? I don't like this alphanumerical way, man. Like, look at this. So left, right is equal to 0, comma. What? Okay, left is equal to 0, right is equal to length minus 1, while should be in here. Should be in here, okay. This is the code, okay. So left comma right is equal to 0, left is equal to 0, length comma string minus 1. Or you could just go minus 1, I think. I could just add on to this one, can't I? So that will be the variables. So while this code needs to run while yeah, this right thing is higher or greater than the left index. Okay, what need to run? Other while loop. While, again same thing, and not this fucking retarded thing, bro. Self alpha. Oh, I don't like this. I don't like this code. Okay, this is the fuck. No, tab. So this is the thing, and not self dot. No, dot. it's a while loop. Okay, it's a while loop. I'm gonna pretend that I didn't see that. Okay. Bro, I don't understand this. I don't understand this code whatsoever. It's supposed to be the easiest two-pointer. Two-pointer again. Give me like an easy problem, bro. I can't understand this.
Hey everybody.
Hey guys, Greg here. Today I'd like to talk about an algorithm known as two pointers. And it's kind of silly because we say pointers, but really we mean indices. So generally what you're doing is given some array, and by two pointers, generally we mean that you have one at the beginning, which I'll call L on the left side, and the other R on the right side. And generally they work towards each other into the middle. Now more generally, two pointers is kind of anything where you have two indices, and so you could also argue an algorithm called sliding window is also two pointers, two of them at the beginning, and they kind of slide across to the end of the array. However, in general, when we refer to two pointers, I actually kind of want to replace this with just called the term squeeze. When most people say two pointers, they refer to one index at the beginning, another at the end, and they kind of squeeze towards the middle. Okay, so to learn about two pointers, we're going to solve the problem called squares of a sorted array, and I'll jump this over to my Jeetcode video where I show how to solve that problem. So we're given an integer array of nums, and it's been sorted in non-decreasing order. I hate when they say that. It basically just means that it's in...
What? What? Okay. Squares of a sorted array 9. No gumbo. Nine sound. Okay, problems, obviously. 977. Let's go. Okay, given an integer nums sorted in a non-decreasing. Non-decreasing means non-decreasing. Who the fuck? Return an array of square of each number sorted in a non-decreasing order. What the fuck does that mean? Okay, I need to square all of this and sort it. Is that what it is? It's supposed to be a two-pointer. Okay. Let me give this shit a shot. So left, comma, right is equal to 0, comma, length of nums minus 1. So if just wanna what am I doing? So while left is actually smaller than right, I want to go on the left side, the index of the left side. Oh, that's actually so useful. Okay, so I need to square this shit, square this, and compare these two. So I want to compare nums. If nums of left is bigger, yeah, if it's bigger, nums of right, let's start with right is bigger than nums nums of left. Okay, if right is bigger than the left, I want to go put the right append the no, that wouldn't work. I need another thing called output. So output is equal to this. Okay, I want to append the square of both of them to the last. So if this is big, this should go first, then this. Fuck. I mean, can I not like sort it already? Can I just like not sort that shit? You know what I mean? Can I not like do that? No, not return. I need to append. No, output. I would append two elements at the same time. Output. Dot append nums of right, square of nums of right. Okay, square. How do I square? How do I fuck? Let's go here. No, don't do that. Don't actually do that, please. I'm about to crash out. When it's not true, I don't give a fuck. Okay, let's. When it actually. It's gonna infinitely like just print it out, don't it? Because right is always gonna be. And I want to go minus, right? I want to left plus is equal to 1, right. This is how it works, I think. Minus is equal to 1. 1, please. And I want to return output. Sorted output. Let's see. While syntax L is not defined. Do you mean L? Oh yeah, left. Not a bad problem though, compared to time exceeded. So, are you guys not going? Yeah, okay. How do I exit the loop? I return else. I return this. I need to take a piss. I should be appending it, right? So append. What? So let me try to print it. Print nums left. I saw ya, bro. So ghetto. The way they talk. Well, because left while, okay, if, oh, obviously, it's never gonna be big. He. And why is it returning the sorted array? Like, what the fuck? Yeah, you got that right, but you need to keep going back again and be like, okay, what is so left, why did I do this? So left still smaller than this thing, and right is still bigger than left. Why is it exiting the loop? Should it go here? Okay, I got my output. I don't have the 0 though. Why is that? So let me like fucking change this shit really quick. So in here we have left, in here we have right. This goes here. Why? Okay, in the middle, when else if, that's where else if comes from, I think. Else if when they're both equal. Let me try another test case to, if I remove this shit, this should be perfectly fine, I think. Kinda, yeah. Yeah, so when it's in the middle, when both are equal, else if left is equal to right, it's gonna, what should I do? I should just return. I shouldn't do the. Yeah, I could just like return the this thing, and yeah, I could just do this. I'm missing a 4 that's in the middle. It is when. Okay, let's print out this thing. Why is it exiting the loop instead of. Or maybe. Groundbreaking, but what of this? What the hell, bro? Why is it not coming here? Maybe we'll cut this out for a second. Or should I go like when the length of list is odd? Do it this way. When it's even, do that way. But it's too much. How do I check it every single second, bro? Expected. No, don't do that. So it was. What? So it was after that. Okay. That's stupid. So initially, when it's 5 index, it's gonna be 0 and 4, 1 and 3. Why does it end? Why does it end? Left is not big. What the fuck? Right is big. Why does it like stop that way? If. Oh, that's why what I see. The actual numbers could be. So 1, 3. It's still big though. I mean, yeah, sometimes it could get like scrambled up. Yeah, I can see why, but I wanna fuck you like an animal. I wanna get you on the inside. I wanna fuck you like an animal. This should be the right chord, I think. Okay, what is going on? Hello? I don't know if it's coming from here though. Comma plus high. Surely not coming from there. So what is going on? else. Should I go else? Maybe. I mean, what is the issue here? I don't get the issue. Don't get the issue. Don't get the issue. Okay, let's look at this, my man.
Increasing, but there might be duplicates. So we need to return an array of the squares of each number, also sorted in non-decreasing order. Again, also sorted in ascending order. So if we were given the array of nums as -4, -1, 0, 3, 10, so it is sorted in increasing order, what we want to do is square all those values. So we'd have 16, 1, 0, 9, and 100, and we want those in the order. So notice they're all going to be positive numbers, because positive and positive makes positive, and negative times negative makes positive. So you want the sorted order of the squares of all of the original numbers. And the reason that's kind of tricky is because originally it's in sorted order, but if you were just to square them, well, it's not sorted anymore. But there's some properties of it where we're going to figure out how to do this well. Okay, so let's use the same example here. Let 100 squared numbers. The easiest way to solve this problem, kind of the brute force solution, is just to say, okay, well, we have the numbers, why don't we just sort it? We could do that in big O of n log n time. You know, it's not the worst runtime, and it would immediately sort it. You could do this in place if you want, or just return a new array, and you are going to get the solution that you'd want, and you could return that, and it'll work in big O of n log n time. Now let's step back to where we got our squares and try to beat n log n. So if you're trying to beat in n log n time, the runtime you're probably hoping is to get rid of the log n part, and you're probably just trying to get O of n. So let's try to get an O of n runtime. Now they're not already in sorted order, but they actually have this kind of clever property to them, where your biggest values are going to be on the outside. So we'll say that we're building up a new array, and the first value will be the biggest value, which is 100. Now we're actually just going to slide this over here, which is why we call this a two-pointer approach. So we're basically using 2 pointers that are tracking these different indices here. They're really indices. And now from this point, your biggest value is either this or it is this. And by the way, I'm going to call this index as L for left, and this index as R for right, or index or pointer. We really mean the same thing here. So we have our 2 pointers L and R. Our biggest value must be either the array at L or it is the array at R. It happens to be the array at L, and so we are going to kind of plug in that we have that value there. That is our second biggest value, and we move L towards the middle here. We have again that our biggest value must be one of these two, either the array at L or the array at R. It happens to be at R. We're going to plug in our value here, and so we'll move R over to the middle. Our biggest value must be one of these two. It happens to be L. We're going to move L towards the middle, and then we would say, hey, we have that they're equal to each other. So we are going to get our new biggest value, which is equivalently our smallest value at this point, because we are actually at the end of the array. At least we've used all the numbers. And here, it doesn't really matter. If your values are equal to each other, we actually have that the array at L is equal to the array at R, and that could have happened at any stage. That actually could have happened if this was a 16 here. If they were, and say R was over here and L was here, it doesn't actually matter which index we used. So we have R and L pointing to the same value. Let's say, for example, that we just moved L over. It doesn't really matter which index we used. Either way, we're going to run into this scenario where R is now not really named appropriately, because R for right is actually on the left. So as in, they've kind of done this crisscross thing that we no longer have that L is less than R. And more specifically, we no longer have that L is less kind of our while this order. Do it with that's basically 0, which is going to go this end. That is the left. Nums at the left squared. Okay, so that's how you do squared in Python. We're adding to the end of the results list the squared of the biggest value.
If absolute equal to, okay.
1 to the left is going to go up by 1 to move it.
Why even equal to? I don't get it.
Center. Otherwise, we're in the opposite case, or they're equal to each other, and so it doesn't really matter what you use if they're equal to each other. So we result dot append the nums at the right squared. Okay, so get that squared value on the right, and right is going to go down by 1 to again move towards the center. At the end of this loop here, we actually have used all of the elements. It's just that we have result in the complete wrong order.
So I'm only moving it at... Okay.
And so you can actually do a result.reverse, which is going to in place without using any extra space. It's going to reverse the order, and then we can just return the result because it's now been reversed. If we run that, that should work just fine. Every single time we run this, we are either moving left or right towards each other, and this loop completes once they crisscross. So basically, you're going to go through all of the numbers, hence we have all of the numbers in the result. Then that is going to be an O of n thing to do, where n is the length of the numbers. After that, we have to reverse, which is going to be O of n time as well. You basically just reverse it in linear time. There's actually a two-pointer way to do that if you wanted to write it yourself, and then you can return the result. So ultimately, this is going to be big O of n. Now, the space complexity is actually a little bit interesting here. So we are storing results, and that's the only thing that we're storing. And while it's extra space because we're storing something that the input didn't give us, we are storing the result that we must actually give back. Like, we literally need to give back this result, so no matter who writes this function, no matter what we possibly do, we're always going to use this space because that is the answer. So if you count extra space as any extra space, then sure, it's O of n, but most people would say that this is O of 1 because we'll ignore the fact that this is actually a part of the return. While I'm not really using any extra space, I'm just using space that you required us to use. Okay, but there's our code. I hope it was helpful, guys. Drop a like if it was, and have a great day. Bye-bye.
That was actually the best way to start, I think. Yeah, this thing, don't really like it. Bro, this is such a bullshit question to begin with. Like, what am I doing with order and all of that? Like, come on. I'm calling another function? Like, come on, bro. Like, come on now. How long have I been streaming? 40 minutes. Fucking kidding me. I need a break already. Fuck. Remove elements. Let's go. Yeah, left 0. Just don't give a fuck. Let's just write length of nums -1 output. I might not need it, but fuck it. I'm going while left is smaller than right, if absolute value of nums, nah, that's the wrong logic. This is the crux of it. Okay, given an integer, any number with integer, val remove. Okay, just give me the examples, broski. 3 value 3, output 2. I need to take all of the 3's out, replace it with this shit. Value 2, take all of the 2 out. Okay. If left or if nums, how do I do a or function? Okay, if nums of left or nums of right equal to val, right? Where the fuck is val, bro? You didn't give the val here. The fuck? Where is val? How do I reset it? Let me copy all this. Reset. That's what I'm saying, bro. You guys are fucking playing with me. Okay, val. What if it is equal to the val? I need to where do I remove nums? I don't even have to. If it is equal, this or that. Okay, it shouldn't be a this or that. It could be both, right? So if the first value is equal to val, if nums is equal to val, and or comma whatever, No, 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 no. If nums, oh shit, not right. Let's go here. If nums left is equal to val, what is going on? Nums left is equal to val. I need to go. Yeah, that's the thing. This gets ended though. I don't want that. I want both of them to like fire at the same. Bro, I used to do a lot of redstone as a kid. Redstone engineering as a kid. I just remember that. It made me kind of emotional. Fuck. I'll do this later. How do I delete? How do I delete it? $27. 27. Easy. 2 pointers. Alright. In progress. Don't do that, please. Can you like not do that at all? Don't. Yeah, okay. This is what I'm working on. I'm gonna come back after a break. Okay, back again. Back. Took like a 10-minute break. Recharged. Ready to rock the wall. Yo, I like this. Let's do another try maybe. Yeah, that'll do. Remove element. Given an integer nums array and an integer val, remove all occurrence in num in place. The order of the element may be changed. Then return the number of elements which are not equal to val. Consider the number elements which are not equal to val be k. To get accepted, you need the following things: change the number of vals such as first k elements. Return k. Oh my god, this guy is a genius, yeah? So, yeah, let's just dive into it. So, the way that I would go about it is, and nums is all of this, val is all of this, okay? Your function should return k is equal to 2. So the value is 3. So if val in num no, it should be, bro, just wanna crumble down and cry for a bit. I'm gonna cry. Okay, who cares? Bro, when you're like actually doing shit, that's when you get like, think about the good old days. You know, think about the good old days, man. Okay, what is going on here? How the fuck am I supposed to do this? Remove element. 27, right? 27, remove element, Python, Java. Who the fuck codes in Java, bro? Who the fuck codes in that? Are you fucking serious? Remove element, lead code. How is 2-pointer used in... Wait a second. How is... fuck! In statistics... and ML. Let's get a toe point. It's 2-point, nigga. 2-pointer. Of course. Efficient finding sorted data, like finding the pairs of a given sum in statistics, computing a percentile for a mean while resorting, sliding window computation for moving averages and correlations. Sliding window and 2-pointers are like pretty connected. Okay. Sliding window is pretty much 2-pointers is basically like you're squeezing from both ends and not trying to meet at the middle, so to speak. And sliding windows kind of somewhat different, I think.
Having solved more than 1500 lead code problems, if there is
1500? Brother, what? You're not even like top 10? What the fuck, bro? You solved 1500, you're not even top 10? Fucking dipshit. 1500, bro. 1500, no BS, no gatekeeping. No fucking way, bro. 1500, what's your Ashish Pati Singh? Patat Singh. Brother, take a chill pill, homie. What the fuck is going on with you? 1500, are you out of your fucking mind? Kegel. I know who you are. Interview IO. Code was maybe.
Why should you have
Linked list. I don't even know. That is linked list. Where is it? Linked list, like 2 chapters away for me to like learn about it properly. And what is going on? I need to find this guy named Ashish. How do I search for you, little bro? Explore. Can I find it that way? That is just insane. Like, you solved that many problems, brother. 400 easy problems. 1,000 medium problems. Oh my god. I think this is like a really good. It's like a normal distribution, isn't it? It's a little bit of a bump. Yeah. This is the ideal.
One thing I've learned is this. Jeetcode is less about the or more than 1500 Jeetcode problems. If there is one thing I've learned is this. Jeetcode is less about the number of problems you have solved and more about how many patterns you know. Because learning patterns allows you to solve a wide variety of problems in less time and helps you quickly identify the right approach to a problem you have never seen before. In this video, I will walk you through 15 most important patterns I learned that made my Jeetcode journey a lot less painful. And the best part is, these patterns actually came up in most of my interviews, including at companies like Amazon and Google. For each pattern, I will explain when to use it, walk
Brother, how long did it take?
through an example, and list Jeetcode problems you can practice to learn them better. First up, we have prefix sum pattern. This pattern is commonly used for problems where you need to query the sum of elements in a subarray. Imagine you are given an array and you need to find the sum of all elements between indices I and j. If you have just one query, you can simply loop through the array in linear time to find the sum. But if you have multiple such queries, it can take up to order of n times m time complexity, where m is the number of queries and n is the length of the array. To make such queries faster, you can create a prefix sum array where value at index I is the sum of all elements from start up to index I in the given array. Now you can also arrange some queries in O of one time using the formula sum from I to j is equal to p of j minus p of I minus 1. This is the main idea behind the prefix sum pattern. One thing to remember is that you don't always need a new array.
So apparently this guy solved 1,583 Jeetcode questions.
When I was in college, I was really struggling with programming.
Yeah.
I tried code forces, code shift, and even tried cracking the coding interview. I never felt ready for interviews. I knew I needed to get better, but I didn't know how. That all
By the way, a really great method to get better is you're kind of worried about interviews, you feel like you're not prepared for interviews. Go and interview at places you don't care about. Start applying to companies you would never work at just to practice. By practicing, and A, you could find out maybe you do actually want to work at that company. Like, that's the best part is A, you could discover something you're really interested in doing, and B, you also just get that practice. You know, there's no amount of Jeetcode you can ever do that's going to make you feel comfortable standing up in front of a whiteboard for the first time. There is no amount of pre-practice. There's no amount of pre-watching. There's no amount of anything to get to that point. You just got to stand in front of a whiteboard to be comfortable standing in front of a whiteboard.
changed in 2017 when I came across Jeetcode. I instantly fell in love with its clean and user-friendly interface. And more importantly, the problems were actually relevant to the real-world interviews.
Yeah.
It not only helped me improve my coding and problem-solving abilities, but also helped me crack coding interviews at big tech companies like Amazon, Google, and Microsoft. In the past,
Shambles right now. I'm literally in shambles. I'm literally in shambles right now. Okay? They could have don't even say it. Don't even say why I'm in shambles, okay? They took the N out of Fang. He just did, right there. Hurts me.
few years I've worked through more than 1500 Jeetcode problems. Mainly because I didn't have anything else to do. And I felt really excited when I got my solution.
Fuck it.
Okay, it feels real bad. I mean, so why did I do them all? I had nothing else to do. So I just built Jeetcode problems.
Questions are accepted, even for the easy problems. I thought more problems I solve, the better are my chances of cracking interviews. However,
not a bad-
that was far from reality. You don't need to solve these many problems.
Yeah,
In this
that's
video,
fair.
I will talk about 3 mistakes I made and the lessons I learned so that you don't fall into the same trap and increase.
By the way, you should do some of them. So I don't know what he's gonna say. I'm curious what his 3 mistakes.
Well, okay, let me just missing positive. First missing positive. Fuck. Yeah, bro. This is like autism. You know what I mean? This is pure autism. Bro, give me this one, this guy. Cracking
Hello,
fan.
and welcome back to the Cracking Fan YouTube channel. Today we're going to be solving LeetCode problem 41, first missing positive. Before we get into the question prompt, just want to remind you guys to subscribe to the channel. We're almost at 2,000 subscribers. Help me get over that milestone. Alright. Given an unsorted array nums, return the smallest missing positive integer. You must implement an algorithm that runs in big O of n time and uses constant space. So, let's look at an example. We have nums, which is 1, 2, 0, and we can see that the first missing positive is 3, because obviously 0 doesn't count as a positive. So, obviously we have a 1, we have a 2, the next number that comes in the positives is a 3, which is not present in the array. That's why our answer is 3. Pretty straightforward. In this nums, we have 7, 8, 9, 11, 12. Obviously, the first missing positive is going to be 1. So that's our answer. Here, you can see that we have negative numbers, but that doesn't matter because we're only interested in the first positive integer. So we have a 1. We have a -1, a 3, and a 4. So obviously, we have 1, 3, 4, and then the gap between those two is going to be a 2. So that's why our answer is 2. Now, this question looks really, really simple on the surface, right? Like, you're just finding the first missing positive, and, you know, let's look at how we might solve this if we didn't have these requirements put on us. So, I mean, the most simple way to do this in big O of n time would simply be to create a set with all of the numbers that we have, and then, you know, we're going to put them in here, so 1, 2, 0, and then what we're going to do is we're just literally going to go from 1 to basically infinity, and the first positive in this range that's not in our set is our answer. Bam, we're done. Unfortunately, while this would run in big O of n time, we use space here, which we can't do. So what's one way we could not use space? Well, we could iterate over all of those numbers again, so from like 1 to infinity, and then literally check if they're inside of our nums here. This way we don't have to use any extra space, but obviously that's going to take big O of n squared time, which is no good. So that solution doesn't work because we have to do it in big O of n time. So how do we actually solve this in a linear runtime and constant space? Well, we looked at how to solve this problem in the naive way, and it's quite simple, but unfortunately we're bound by a linear runtime and a constant extra space, space complexity. So that makes things a little bit harder. And what we're going to do here is we're going to use our values inside of the array to basically...
What is going on? Come on.
Obviously, 1 is the first missing positive integer.
Brother.
It's not even in our array.
Just yapping, never getting to the point. This guy, you know what I mean? It's a short video.
प्रॉब्लम है और फिकी भी, बट हम लोग इसको आसान बनाना। फर्स्ट है कि नेगेटिव नंबर्स आर नॉट यूज्ड। सेकंड में हम लोग को जो ध्यान रखना है कि जो फर्स्ट मिसिंग पॉजिटिव नंबर रहेगा वो 1 से लेंथ ऑफ लिस्ट प्लस 1 नहीं रहे। जो गिवन एरे है हम लोग उसको ही एसेट बनाना है। टाइम कम्प्लेक्सिटी हो रहा है।
Yo, jabali la la jona.
Coming to our next question, it's an interesting one. How many lead code questions did you solve?
So around 125 to 150, which was enough. I followed the cryos sprints.
Okay.
There was DSA 1, 2, 3, DSA 3 light.
Yeah.
So I just followed those. So around 125.
For you?
I think I've done close to 130, 140 questions. After cracking the interview, I've stopped.
What about you?
135.
135. I also believe that if you have to cover up all the concepts, I think near about 150 is standard. If you don't know DSA from the basic, then you have to. That's a different story. But if you're preparing, I think covering up 150 around should be sufficient because I think the concepts are very limited. And the only thing that I'll say everyone is don't mug up every question. Any question that you do not mug up. Instead of it, take concepts that will actually help you. If you take 150 concepts from 150 problems, that actually covers most of the things. Coming to our next question, it's an interesting one. How many lead code questions did you solve?
So around
Jeet.
120.
Jeet. You're a Jeet. Okay. Should I? What should I do? Bro, coding concepts, heap. I don't want to do none of them. I don't want to do none of them. I just want to. Okay, let me just watch a math video. Let's just. I don't know.
This one video is going to explain all of these questions for you. How does AI work? How does AI learn? How does ChatGPT work? How does image generation work? Does AI actually copy or steal art or other content? I know a decent portion of artists out there do not like AI. Some of them are quite hostile towards AI because they think that AI is stealing their work or their art style. Another group that does not like AI very much are, for example, publishers. I'm not saying all of them, but some of them, like New York Times, for example, they claim that OpenAI is copying their content and they're now suing OpenAI for this. But is this really the case? Is this a valid argument? Also, can AI a project that OpenAI was working on? Now, whether this is true or not is not the point of this video, but this document was quite controversial because it claims that this team trained an AI that was able to break encryption systems. These are systems that secure our passwords, our bank accounts, the internet, government data, etc. Now, as far as we know, there's no mathematically viable way to really hack this systematically. The only way is to brute force guess all the different possibilities of passwords. This video will explain, can AI actually do this? Can it actually break encryption or solve these other math problems which right now we believe are mathematically unsolvable? Also, we'll talk about, can AI beat humans at everything? Can AI eventually be so good that it can outperform humans at any task? And finally, is AI conscious or self-aware or sentient? Make sure you stick to the end because the explanation to this is going to be very juicy. We'll cover all of this in easy to understand terms. Now, if
easy to understand.
This one video.
Brother, what the fuck are you talking? MLP? What is an MLP? What is RQ? What is... Reinforced learning? Fuck, I gotta watch a Crash Course video.
Bro, and welcome
But what is this nigga doing here? Like, what the fuck?
to Crash Course AI. Say I want to get a cookie from a jar that's on a tall shelf. There isn't one right way to get the cookies. Maybe I find a ladder, or use a lasso, or build a complicated system of pools. These could all be brilliant or terrible ideas. But if something works, I get the sweet taste of victory, and I learned that doing the same thing could get me another cookie in the future. We learn lots of things by trial and error, and this kind of learning by doing to achieve complicated goals is called reinforcement learning. So far, we've talked about two types of learning in Crash Course AI. Supervised learning, where a teacher gives an AI answers to learn from, and unsupervised learning, where an AI tries to find patterns in the world. Reinforcement learning is particularly useful for situations where we want to train AIs to have certain skills we don't fully understand ourselves. For example, I'm pretty good at walking, but trying to explain the process of walking is kind of difficult. What angle should your femur be relative to your foot? And should you move it with the average angular velocity of... yeah, never mind.
It's really difficult. With reinforcement learning, we can train AIs to perform complicated tasks. But unlike other techniques, we only have to tell them at the very end of the task if they succeeded, and then ask them to tell us how well they did. We're going to focus on this general case, but sometimes this feedback could come earlier. So, if we want an AI to learn to walk, we give them a reward if they're both standing up and moving forward, and then figure out what steps they took to get to that point. The longer the AI stands up and moves forward, the longer it's walking, and the more reward it gets. So, you can kind of see how the key to reinforcement learning is just trial and error over and over again. For humans, a reward might be a cookie or the joy of winning a board game, but for an AI system, a reward is just a small positive signal that basically tells it, good job, and do that again. Google DeepMind got some pretty impressive results when they used reinforcement learning to teach virtual AI systems to walk, jump, and even duck under obstacles. It looks kinda silly, but works pretty well. Other researchers have even helped real-life robots learn to walk. Seeing the end result is pretty fun. It can help us understand the goals of reinforcement learning. But to really understand how reinforcement learning works, we have to learn new language to talk about these AI and what they're doing. Similar to previous episodes, we have an AI, or agent, that is our loyal subject that's going to learn. An agent makes predictions, or performs actions, like moving a tiny bit forward, or picking the next best move in a game. And it performs actions based on its current inputs.
How did... Wait.
We call the states. In supervised learning, after each action, we would have a training label that tells our AI whether it did the right thing or not. We can't do that with reinforcement learning because we don't know what the right thing actually is until it's completely done with the task. This difference actually highlights one of the hardest parts of reinforcement learning, called credit assignment. It's hard to know which actions helped us get to the reward and should get the credit, and which...
About 2 years ago, I set out to build my own chess computer. The idea of writing a program that could beat me at something I do quite regularly was very intriguing, and it turned out to be one of the best programming experiences of my life. I found so much elegancy, and the overall experience of building and iterating on it was very satisfying. The very first thing we have to do is to think about how we're going to represent a chess position, programmatically. Our initial instinct might be to encode the pieces in some way and store it in an array. But there's a much more efficient method we could use, the bitboard method. Bitboards capitalize on the fact that a chessboard has 64 squares, and a 64-bit integer also contains 64 bits of information. So we can represent the position of, say, all white pawns with one large number, where each bit corresponds to a specific square on the board. If we now want to check if some square is occupied by any of these pawns, we can simply take that square bitboard, perform a bitwise AND operation with the pawns, and check for a non-zero result. It's things like this which enables the generation of possible moves, and when you're searching millions of positions a second, a significant amount of time is spent here. What we did now amounts to a handful of CPU instructions, so it's really fast. Finally, the whole board could be represented by 12 of these bitboards, one for each piece, along with a few game rules. Before we can go and find the best move, we have to somehow be able to tell if a position is better than the other. We need an evaluation function, one that takes a chessboard's input and outputs who's doing better. Some positions are straightforward, like when someone has checkmated the other or when it's a draw. So let's start here. We're going to assign a large arbitrary number when white has won, and the negative of it when black has won. A draw will be 0. When the game is yet to be decided, it's more tricky, but generally, capturing pieces indicates a strong position. So for starters, we assign values to each piece. A pawn will be a1, and all the other. But let's not stop here. We can give our evaluation function a little more nuance by considering where a piece is located. See, a knight in the middle is better than one on the edge, as it controls more squares.
Yeah.
So for each square, we can adjust that piece's value by some amount. So now when we count the material, this knight will be worth 3.25, and this one 2.5.
Same with like convolution,
we can do this for all piece types.
edge
For
case
instance, a king
detection
generally wants
in
to be tucked
images.
away in the corner. These adjustment values makes a tremendous
Bit board.
difference.
Okay.
It makes the engine make natural moves, placing pieces on active squares and prioritizing king safety. Even though this way of defining a position's value is hard-coded, it is very sufficient for creating extremely strong chess engines. And the reason for that is search. We start by extracting all the legal moves.
Bro, that's crazy.
We then make those moves and use the evaluation function to get a score. We do this for all the moves, and it seems like taking the pawn is the best move. However, if we calculate further, the black king will capture the rook, resulting in a draw. So taking the pawn is of course bad, and you should move your rook. Had we taken black's response into consideration for every move, moving the rook would have maximized the eval. And this is what it's all about, searching down the game tree. But now, let's do it properly with the famous minimax algorithm. As input, it will take in a board and a depth, indicating how deep we'll search. And it will return the best achievable evaluation. To demonstrate, we will search to a depth of 2, meaning white makes a move and black responds. Or in other terms, we will consider white's moves and then black's responses to those moves. Nodes will be orange when it's black's turn to move.
It's depth for search.
So let's
Okay.
call minimax on the starting position and initialize
Okay. Minimax algorithm.
for this
Cool.
too. Since the return value is lower than what we have found so far, we will assign it as the new best. We do this for all the moves, and eventually when we're done, we're going to return that evaluation, taking it back to the starting position. Just like with black, let's save the result, compare it, and do this procedure for the remaining moves. If we take a closer look and rewind a little bit, just when white evaluated the first branch, then went down this path and found a -4, we know for sure that this node will be -4 or lower, since it's black choosing the moves. But since white has already found a -2, they will never go down this branch, and so there is no need to evaluate the remaining positions. We can prune the search tree. We would do this by implementing the alpha-beta algorithm, where you keep track of the best eval each side. But this was the very core of a chess engine. If you ever do decide to embark on this journey, there's a whole Wikipedia about all of this. I wish you a happy day.
So fucking hell, bro. Fascinating. So what do people actually like do? Like how do they? Do you have to? Fuck. Fuck, that's actually like fun as fuck. I want to make something to do with chess. A real world solo. Tom, one of the stockfish creators, started solo. His early engine become the solo. A small teams example. Okay, that's cool. How does it actually work though? I think it's lot a bitmap board, as he said. What is a bitmap board? Can I nigga get a coding make A better chessboard. Can I do that?
Using bitboards. So a bitboard is really just a single number that represents some aspect. Yeah. Alright. Is about 20% slower. Alright, so all the slating pieces are now using the magic bitboard approach, and but anyway, let's just try a few more quick things.
Hey, what's going on, guys? Make Games here. In this video I'd like to announce the beginning of the new series introducing a bitboard chess engine video tutorial series, starting from scratch, absolutely from scratch, and ending up with a chess engine that actually can play versus other engines using the UCI protocol. And before... Hey, what's going on, guys? Make Games.
What is it? Bro, I swear.
Okay, so I will now try to apply. Okay, so I'm
Bro, I could like it. Yeah, it's decent though. It's decent.
Hello everyone, in this video I'm going to be playing Perk Defense, which my teacher considered to be an open...
Perk Defense. Lame. Bro, I can get there. I think I'm like 1,800 at my peak. I can get there. Not a big deal.
Hello everyone, in this video I'm going to be playing Perk Defense, which my teacher considered to be an opening for black for all occasions.
Hi everyone, this is another test. As I made a chess game in C# in Unity called Chess Tools, I kind of, well, I don't know, not really an expert, but I made a chess engine in that. I know how to do it, and I thought it's a very good way to test performance. So I decided to do it in lots of languages. So this is basically me converting my bitboard chess.
Bro, there's like so many like things.
Generate chess move generator into loads of languages to test performance, and also trying to compare how easy it is to actually implement such an algorithm in different languages. So first I should say performance isn't everything with languages. It's normally a cost-benefit analysis which languages are used for different purposes. It's not just performance. For example, Python is extremely slow, but it's also very practical, easy to use, and has also many practical libraries. So it's not really speed that's the point. Whereas C++, the whole point is speed, so it kind of depends on what the purpose of the language is, and also if something's ridiculously hard to learn, but its speed is like, it's kind of like a trade-off between those things. So speed isn't everything. Also, this is a very specific task. It's very, very CPU intensive. Most tasks aren't this intensive, and you don't need this much speed. Here's just an explanation of how the bitboard algorithm works. So here we have a basic chessboard, and we want to represent this in code. So normally what we'd use is just an array. So we use a 64-element array, like this, with integers, like this. Explaining how this works. Variables anyway. So like I call perf inline global u128, 128 bits. Or you have to use this to spec It's everything readable. I know there's a mod of Python that makes you can use curly braces. I couldn't be bothered to install it. It's easier just to use means and just do this. Anyway, yeah, so Python, it's pretty slow actually, but I got it working. I mean, other than that, there's not really much difference. I mean, recursion works pretty well, and yeah, it's pretty much the same. Alright, and here we get to Rust, which was easily the hardest to get working imaginable. I'll try not to make this a rant, but oh my god, it took me about 3 days, and a lot of debugging, a lot of spamming ChatGPT to get this to work. So what's the main problem? I'll show you. Okay, I'll show you what happens. So I just made a PowerShell on this window, cargo run, get it to warning, says the named. Oh, what's this? Thread main has overflowed its stack. What? Why does it mean it's overflowed its stack? In every other language, it didn't overflow its stack. Why would it have a stack overflow? Oh, because we're in debug mode. And for some reason, also like ChatGPT release, and it works. It doesn't give you stack overflow. So that was one problem with Rust. Then I tried to separate it into modules, but then I found the module system is terrible. It's absolutely terrible. I don't know why they designed it this way, because everything's interconnected. So you say, for example, you have like, I don't know, you have the main script, then you have the board script, and you have the constants, and then you have, I don't know, the perf script, and they both want to.
Okay. That's how it works. What AI does it use? Like what kind of... It's chess engines. No ML pure search, no handcuff evolution compound. Hybrid engine, modern starfish, Komodo dragon, uses integrated neural network evaluation. So it is pure on net. Okay, alpha 0. These reinforced learning, huh? So what is reinforced learning? That is like one site. This one? No. This one? This one?
Hello everyone. In this video, you'll learn.
So it's a lot of reinforced, fastest introduction to reinforced learning. Okay, let's just take a look at it. So reinforced learning is just like, why is that not better? Why is...
Computers are good at doing exactly what you tell them to do, which is both a blessing and a curse. If I want to add two very large numbers, that's perfect. The computer can do that. But if I want a computer or robot to do everyday tasks like tie a shoe, fold a t-shirt, or even just walking, it's impossible to specify exactly how to move its joints and interact with the environment, and exactly what the forces, masses, and friction of the physical world are. Reinforcement learning is a field of machine learning that tries to solve precisely that. It's quite appealing to people because of how it resembles the way that humans and animals learn in the physical world, through trial and error and using positive and negative reward to reinforce the behaviors that you want and punish the behaviors that you don't want. In recent years, some of the achievements of reinforcement learning include learning to play Atari games in 2013, defeating top human Go players in 2016 with AlphaGo, defeating professional Dota 2 players in 2018 with OpenAI 5, solving a Rubik's Cube with a robot hand by OpenAI in 2019, certain applications in robot dogs, self-driving, fine-tuning language models, etc., and all those AI learns to YouTube videos, of which I have made one as well. This video to YouTube videos, of which I have made one as well. This video is over an hour long, very dense in information and not very entertaining. Its purpose is to help those who are interested learn as much of reinforcement learning as possible, as easily as possible, and as fast as possible. This is because I think that this technology and this field of study will be very important in the next few decades, when artificial intelligence gradually brings its capabilities to the physical world, and I want to make the knowledge as accessible as possible to all people. We will go over much of the foundational theory and math, while demonstrating it in practice with a series of example tasks that gradually increase in complexity. That will be the bulk of the video, and then following that, we will cover the interesting correlations between reinforcement learning and neuroscience, and how the brain works. And then we will talk about the aspects in which reinforcement learning is still lacking, and some of the directions of future research that I think will be of great help. This video is not meant to be watched just once, so feel free to re-watch it as many times as you need to extract its value. The prerequisite knowledge of this video includes maths up until basic calculus and a basic understanding of neural networks. In order to research for this video, some of the main sources of information I used include the book Reinforcement Learning: An Introduction by Sussman and Bartow, which is widely regarded as the holy bible of reinforcement learning, the OpenAI Spinning Up website, which has compiled a lot of information about the most famous and influential algorithms, large language models such as ChatGPT, which are really good at searching for, compiling, and summarizing widely known knowledge, and the reinforcement learning subreddit, where you can read through other people's questions and answers on the topic. As well as these resources, I'll leave a link to some of the interesting articles that I mentioned in this video in the description. Now, before we begin, have a look at my hair. I've chosen to film the introduction at the very end, and throughout the different segments of the video, you'll notice that my hair has grown quite a bit. Indeed, this video was approximately half a year in the making, with even just the filming spanning several months. And no, I didn't avoid haircuts just to prove a point, I was just lazy, but if you watch through the video and find value in this, consider supporting the channel on Patreon, link in the description. I've put some of the behind-the-scenes demo videos on there as of now, but those are in this video anyways, so consider supporting if you're interested in topics related to AI and robotics, and you'd like to see behind the scenes of future videos. With that being said, let's get started. In reinforcement learning, which I'll refer to in the rest of the video as RL, there is an agent and an environment. Agent is the car, environment is the road. Agent is the player, environment is the map. Agent is the hand, environment is the cube, and agent is the strategy, environment is the chess match. The definition of agents and environments, which generalizes to all these situations, is that you can say the agent is whatever you can directly control, and the environment is whatever you cannot directly control, but you're trying to indirectly interact with through the agent. Now, when the agent interacts with the environment, obviously there's two directions of influence. Influence of the agent on the environment is called an action, and as a human you can intuitively think of the movements in your limbs and your muscles. Influence of the environment on the agent is called state, and as a human it's your sensory input. You're observing the state of the environment. As a human, the sensory input and motor output loop is kind of like a form of this agent-environment interaction, where the brain is the agent, responsible for integrating data and decision-making. In RL, we're trying to create such an agent, such a brain, using a computer. So of course all these states and actions have to be represented as numbers. The state could be position and velocity, colors of pixels, temperature, battery level, etc. And the action could include numbers representing how fast to spin a motor, which direction to go, which ability to activate in a video game, etc. Now remember, where exactly you draw the boundary between agent and environment is actually more nuanced than you might think, and it depends entirely on your realm of control and what specific task you're trying to achieve. Only what you can directly control, what you can take for granted, is the agent. For example, imagine I'm learning how to drive a car, but I'm starting from zero. I don't even know how to move my limbs yet. We need to write a program. Let's call it Program A, and put it in my brain in order to learn how to move my limbs. Here, what we can directly control are the neuron signals that my brain sends down my spinal cord into my muscle. What we cannot directly control, but are trying to influence indirectly, are the movements of my limbs. So we can say the agent is my brain, the environment is my limbs, the actions are my neuron signals, and the state includes the positions, joint angles, and movements of my limbs, as observed through visual feedback and proprioception. Now pretend we've fine-tuned this program enough, so now I'm pretty confident with limb movements. In my forearm, for example, I can open and close my grip, do some wrist flexion and extension, and occasionally, if I'm feeling extra adventurous, maybe even dabble in some ulnar and radial deviation. Now
No, what are you doing? What the fuck are you doing? Why are you reloading? Are you fucking retarded?
Welcome back. In this video, I will discuss
Now we have to write program B to control how I'll interact with the car. The agent is me as a living creature, the environment is the car, the actions are my limb movements, and the state consists of the elements of the car, which I can observe visually, such as looking at the speedometer, or through tactile feedback, like gripping the steering wheel, or stepping on the brakes. Now that I know how to operate the car, I have to learn to drive using program C, which, let's say, can now directly control how the car moves forwards and backwards, and how it turns. Now the agent is the whole car, the environment is the road, the actions are just how the car moves, and the state includes other cars and their positions, how many lanes there are, what the speed limit is, etc., which I observe visually. So in this agent environment model, the boundary between agent and environment can be quite arbitrary, and the time scale for these actions and state observations can also. The environment is the road, the actions are just how the car moves, and the state includes other cars and their positions, how many lanes there are, what the speed limit is, etc., which I observe visually. So in this agent environment model, the boundary between agents and environments can be quite arbitrary, and the time scale for these actions and state observations can also be quite arbitrary. Like, for example, if I close my fist, is that one action, or is it 5 actions, one for each finger? The good thing about this arbitrariness is because you can frame a problem in so many different ways, you can choose to frame it in a way that gives the problem structure and makes it easier to solve. So let's go over the way that reinforcement learning frames a task in order to solve it, which is called the Markov decision process. So first of all, there's also this added signal known as a reward, which is just a single number that comes after each action that represents whether that action had a good or bad outcome. The more positive the reward, the better, and the more negative the reward, the worse. Now, it's up to you to interpret whether the reward comes from the agents or the environment. If it's a human learning something, we can generally decide for ourselves whether we did good or bad at that task. But if you're training a dog, then the reward of food seems to be provided externally. Conventionally, the reward is considered to be a signal from the environment to the agent. So let's stick with that. So now let's write out what a Markov decision process is, also known as an MDP. It's a discrete, repeating, one after the other sequence of state, action, reward, state, action, reward, state, action, reward, and so on. This can either go on forever, or it can terminate, like if you're playing a level in a video game and you die on that level, in which case it's called an episode, and the episode terminates.
Just a small note on the notation. Here I've chosen to have the time step of the reward take on the time step of the state and action before it. So it would go S0, A0, R0, S1, A1, R1, etc. This is because I thought it makes more sense this way. However, I found out that in other sources about reinforcement learning, usually they have it so the rewards time step is the same as the state and action after it. So it goes S0, A0, R1, S1, A1, R2, etc. This is not a huge deal, but as a result, in some of the later mathematical formulas, you might see that it's a bit different compared to those formulas in other sources, where the time step of the reward is off by 1. Other sources also often choose to use uppercase letters,
like capital R, but here I've chosen to use lowercase r. Once again, not a big deal. Let's get on with the video. Ideally, this sequence must follow a rule called the Markov property, which means that each state is only dependent on its immediately previous state, and not any other states. For example, if you're making a robot to catch a ball, and you've designed it so that the state information it receives only includes its position, then it's unclear what the next state will be, because it's unclear in which direction and how fast the ball is moving. You would have to look at multiple consecutive states to deduce that information. If instead you also included the velocity in the state information, then it would follow the Markov property, and each state is only determined by the immediately previous one. Of course, the robot isn't necessarily going to know how gravity works, or how one state transitions to the next, but at least there's sufficient information for it to learn that. Now, MDPs, are they perfect? Do they apply to every single situation? Probably not. First of all, lots of RL methods rely on this Markov property so that they can just go off of the most recent state to decide on the next action and keep it simple. But obviously, not all situations are going to satisfy this Markov property. And if we have certain states that depend on more previous states, then the tools that we develop using this framework aren't going to work as well. Also, with a simple sequence like this, it's hard to deal with varying timescales. If you want to work on the scale of individual muscle movements in one moment, and then in the next moment zoom out to, let's say, which city to drive to, then you'd probably need a more complex framework than that. Another thing is, there's only one single number as a reward signal. If you're doing tasks that are more nuanced and can be evaluated in multiple aspects, then maybe having only a single number as a feedback for each action can be a bit limiting. But this is pretty much the best that we've been able to come up with so far, and basically all of reinforcement learning is built on the foundation of MDPs. Maybe in the future, someone could figure out a way that works better. Maybe that could be you, the viewer. But anyways, let's talk about some of the maths in an MDP. Within an MDP, the ultimate goal of the agent is to figure out how to, for any given time step, use an input state to decide on an output action in a way that maximizes the total subsequent reward over time. So let's cover these two mathematical constructs: the strategy that takes a state and decides on an action, and the cumulative reward over time. The strategy, we call that the policy function, represented by the symbol pi. You can intuitively think of it as a mathematical function that takes a state as an input and gives an action as an output. But technically, the notation for this policy function is usually written a bit differently to allow it to have some randomness. As in, given the same state, the policy can produce a range of different actions, each with their own probability. The randomness is important for exploring different strategies. So RL people usually write the policy function as giving the probability of picking a certain action given this vertical bar is a conditional, given that you're in a certain state. Now the next thing, the total cumulative reward, is called the return, represented by capital G with a subscript T. The subscript T represents which time step it's for. So for example, if we're talking about the sum of rewards starting from R1, then that would be G1. This is just all the rewards added up, starting from time step T, and progressively multiplied by this discount factor gamma in increasing powers. Now, gamma is just a number between 0 and 1, and this can be lowered to make rewards in the future less significant, perhaps because the future is inherently harder to predict. So maybe you'd want that to factor less into your decision making. Or gamma can just be set to 1, in which case this would be an undiscounted sum. But then it would only work for terminating episodes, or else it'll just add up into infinity. Of course, it's better to try to maximize the total reward over time instead of just the immediate reward for a single time step, because what gets you more reward immediately might make you get less reward later on, kind of like delayed gratification. So remember how the goal is to, for any given time step, use an input state to determine an output action in order to maximize the total subsequent reward over time? Using this mathematical terminology now, we can instead say that the goal is to find the policy which maximizes return. Find the policy which maximizes return. Alright, let's try applying this to a practical example. Usually, when you're teaching RL, you start with some sort of task involving a grid, and we're going to do that too. The reason is that even though no real-life problem will ever be this simple, in a grid, each state corresponds to a single square. So it's really easy to visualize and demonstrate some key concepts, like the exploration-exploitation trade-off, temporal difference, the credit assignment problem, world models, and sample efficiency. Using our simple grid demo, we're going to go through what each of these terms mean, how they relate to each other, and why they're important for reinforcement learning. We have a maze, well, a really simple one with just one wall, but let's still call it a maze, where the agent starts on a certain cell and must get to the target cell by moving up, down, left, or right. And it cannot move through walls. The maximum episode length is 20, so the episode terminates when it either reaches the target or when it's been going for 20 steps already and still hasn't reached the target. Let's start thinking about how we can apply the theory we've developed so far and frame this task as a Markov decision process. So first, we'll need to define a state, action, and reward. So each state will be two numbers representing the XY coordinates that the agent is on. Each action will be a single number between 0 and 3 representing either up, down, left, or right. The reward after each action will be 0 if the agent enters the target cell, or -1 otherwise, which makes it so that the goal is to arrive at the target as fast as possible. So here we can talk about our first concept, which is world models. As humans, we can obviously see the whole maze at a glance and immediately figure out how to solve it. Because we understand that the states represent coordinates, the actions represent directions, and how the reward works, we know that if you're in the state of 0, 0, and you pick the action of 3, representing right, that you'll move into 1, 0, and get a reward of -1. We also know that in 1, 1, if you pick 3 and try to move right, then you'll stay there because there's a wall in front of it. If the agent also understands this, then we say that it has a world model, or a model of the environment. Mathematically, this just means having access to this function, sometimes denoted as P, which tells you, given that you picked a certain action in a certain state, what reward and next state will it lead to? Or more precisely, to account for some randomness in the environment, what's the probability of any next state and reward given a combination of being in a certain state and picking a certain action? A function like this is an example of a world model. It turns out that whether an RL agent has access to a world model, whether it understands how the world works, makes a massive difference to how well it can learn to do tasks, which obviously makes sense. This is also why a lot of the current research in RL is concerned with how to develop better world models, or make agents learn better world models on their own for complex tasks. With our maze task though, we're gonna start by focusing on model-free methods, which assume that the agent does not have access to a world model. In other words, the agent cannot see the whole maze at a glance like us humans. It doesn't know what the state and action numbers represent or how they relate to each other, and it doesn't understand how the rewards work. So it doesn't know that if you're in 0, 0 and you pick 3, you'll end up in 1, 0, for example. The states, actions, and rewards are just meaningless random numbers, and the agent has to somehow learn to pick actions in a way that maximizes the rewards it gets. So without access to any information, all the agents can do at the start is just randomly pick actions, meaning that instead of using a policy where there's actually meaningful probabilities for the different actions, it's effectively using a policy that looks like this. For all these meaningless input numbers, all the meaningless output numbers have the same probability, and we're meant to somehow improve this policy over time. So by picking random actions, of course, most of the time it gets nowhere and receives a total reward of -20, since the episodes are capped at 20 steps. But the important thing is that it's writing down all of its experiences in order to learn from. This process of trying actions is called sampling, and all these sequences of state action reward are known as trajectories. The agent is collecting sample trajectories. Eventually, due to shear lock, there will be a few trajectories where it actually does reach the target, and these are the important ones. Let's see how the learning happens. But first, we're going to now use this other mathematical concepts that we've developed and calculate the returns for each time step in our successful trajectory, using a gamma of, let's say, 0.8. The way we can do this, because of the way that later rewards are progressively multiplied by gamma, is we can start at the end and work backwards. The return of the last time step will just be 0. And to get to the previous one, you multiply that by gamma, and then add on the previous reward. Then, to get to the previous one, you multiply that whole sum by gamma, and add on the previous reward again. Then you repeat. In the end, you'll find that even though this is a successful trajectory, all the returns are negative, because all the rewards are negative, obviously, except for when the agent reaches the target. But in the unsuccessful trajectories, all the calculated returns are going to be even more negative, because the agent never reaches the target, so it keeps collecting the -1 rewards for the full 20 time steps. So now that we have all our sample trajectories and we've calculated the returns for each time step, we have to somehow use these experiences to achieve a better policy. There are different ways that you can go about this. You can directly work with these probabilities, for example. Push the probability up for actions that had good returns, and push the probability down for actions that had bad returns. That would be called a policy gradient method. Gradient meaning rate of change, and we have to calculate how much to change the policy based on which actions are good and which actions are bad. But doing that requires us to know what's considered good and what's considered bad. Consider this example where we have 3 actions initially all set to the same probability. Let's say we collect a lot of sample trajectories, and on average, action 1 gives a return of -5, action 2 gives a return of 0, and the third action gives a return of 5. Then it's pretty straightforward. You push the probability for action 1 down, keep action 2 roughly the same, and then push action 3 up. But what if instead action 1 gave 5, action 2... 2 gave 10, and action 3 gave 15. Or what if it's 95, 100, and 105? Or if it's like our maze example, where everything's negative. See, the issue here is not that all three numbers are positive or negative, and you can't increase or decrease all probabilities and still have them add up to 1. When you're actually using policy gradient methods, the effect on the probabilities is more like a tug of war, especially with neural networks, which have this thing called a softmax function that makes sure everything adds up to 1. The real issue is that proportionally, the effects are now different. 10 to 15 is a 50% increase, while 100 to 105 is only a 5% increase. What we want is for all cases to have the same effect, because an increase of 5 is an increase of 5 no matter what, especially since within the same environment, maybe some states are just better on average, and some states are just worse on average, no matter what action you take. So what we need is these things called value functions as our baselines, which keep track of the average return you should expect to get when you're following a certain policy, and help evaluate how good or bad states and actions are. V is the state value function, representing how much return you should expect to get when you're in a certain state and follow a certain policy. Q is the action value function, representing how much return you should expect if you're in a certain state, pick a certain action, and then follow the given policy. Notice that these functions necessarily have a policy function attached to them, because if it's a different policy function, the actions that are picked will be different. So naturally, you would expect to get different returns. These are just random example numbers that I made up, but the key is that it's different for different policies. In fact, the state value function is basically just all the action values within that state, averaged according to the probabilities given by the policy. If you just want to not care about which specific policy it's talking about, and refer to what's the best case scenario if you somehow picked the best action every time, then that would be V star and Q star, the optimal value function. We've written these value functions not as probabilities without any randomness, unlike the policy and world model up here, because RL is still developing, and up till now, people have not yet considered randomness and variance for the value functions as much. There are fields of research though, like Bayesian RL and distributional RL, which do consider variance in value functions, which you can think of as like risk to reward ratio, as in how good a state or action is, but also how uncertain that goodness is. There are so many unanswered questions in RL. But anyways, that's our value functions. Once we have our value functions, then we can improve our policy. And now we have a few different options as to how we do this. First, we could just use the policy gradient method we talked about before without using a value function baseline. There's issues with that, as we've said, with the different averages, it doesn't work that well. And then we could also use the policy gradient method with a baseline, such as our state value function, to compare with all the different returns in the same state. Now this works better as all these cases with different averages can be made to all have the same effect. But it turns out there's also another method, which is instead to just look at the